Hello everyone, thank you for coming to my presentation. My name is Yifan Wang. I'm a PhD student at Stevens Institute of Technology. Today I'm going to talk about our work facilitating parallel fuzzing with mutually exclusive task distribution. In recent years, fuzzing has become really popular. It is considered as one of the most effective way in finding the security bugs in software. So for example, EFL fuzzing has already found thousands of the bugs in open source projects, and because of such successful attempts, many big firms invest a lot of computing resources in large-scale parallel fuzzing. However, most of the parallel fuzzing without elaborate distribution of the workload. This can lead to different instances to explore overlapped code region and reducing the benefit of the concurrency and wasting the computing resources. So we propose a general model to describe the parallel fuzzing. And also guided by this model, we developed a solution called EFL Edge to improve the parallel mode of EFL, elaborate the workload among the instances, and enhance the efficiency eventually. In this research, we target the gray box of fuzzing, the most popular category of fuzzing. It follows the feedback scheduling mutation model and presents an iterative process, starting with a queue of seed inputs. In a round of the fuzzing, the scheduling picks a seed and feed it back to the mutation process for deriving the new input to test the target program, expecting to trigger the unhandled crashes or exceptions. Both the scheduling and the mutation process are based on the feedback from the program execution. Also, the fuzzer based on the feedback to decide whether an input under the test should be added to the seed queue or not. To improve the efficiency of the code coverage, many gray box fuzzing tools provide the parallel mode to run the multiple instances concurrently. Depending on the implementation, different instances may either share the same seed queue or carry the separate seed queue, but periodically exchange the seeds. In the latter case, each instance borrows from other instance all the seeds that bring new code coverage. So this is the gray box of fuzzing and the parallel mode. The idea of sharing the seeds across the instance is actually an intentional design of AFL. The goal is that the hard to hit but interesting test cases can be used by all the instances to get their fuzzing work. However, the intuition suggested that such a design can lead the different instances to mutate the same seeds, which may eventually reduce the effectiveness of the concurrency, right? To validate this intuition is the motivation of our research. In our motivation study, we run AFL on 4 popular benchmark programs with 2 parallel instances for 24 hours. We trace the mutation process to understand which seeds are mutated by which instance. So as shown here, the different instances are indeed mutate overlap seeds, while many other seeds never been mutated. So consider the result after 6 hours as an example. On the average, nearly 20% of the seeds are never being mutated. However, over 42% of the seeds received multiple rounds of the mutations. From this experiment, we know that the parallel fuzzing definitely would bring in the overlap, right? To verify whether the overlap would lead to the worse fuzzing efficiency, we conduct another experiment. We randomly collect 1,000 seeds produced in above test from each program and equally split the seeds into Group A and Group B. First, we run EFL to mutate Group A for multiple rounds, and we calculate the increase of the code coverage after each round of the mutation. Here we use the CFG edges as the metric of the code coverage, and we consider the edges covered by the original 1000 seeds as the baseline. Then we repeat the experiment, but replace the same X% of the group A with unmuted seeds from group B in each round. So for example, when we set X to 10, we run the original group A in the first round, but in every following round, we replace a fixed subset of 50 seeds with other unmutated ones from group B. Such an experiment enables us to simulate the fuzzing scenarios where a different extent of the overlapped mutation happened. So here's the figure. We can see it presents the result of the experiment under different settings. With all the 4 programs, we observe a trend that fewer overlaps among the mutated seeds lead to a higher increase of code coverage. So this demonstrates that running AFL's mutation on different seeds can cover more edges than running the mutation on the same seeds. So it is therefore necessary to investigate and develop better solutions for the parallel fuzzing. So at beginning, we propose a model to describe the parallel fuzzing. The model it's inclusive of the parallel mode in existing fuzzing tools, and it is general enough to apply to other solutions of the parallel fuzzing. It has 3 properties. The first one is the different instance should work on disjoint subset of the tasks. This is to avoid the overlap and increase the extent of the concurrency. The second one is all the instances together should cover all the tasks. Otherwise, the pursuit of the parallel fuzzing can cause the loss of the certain task cases, essentially gonna miss the code that can be covered by those task cases. The last one, the different task cases should be assigned with a similar workload. Otherwise, the certain instance can receive the underloaded task and end with the plenty of the idle circles, which also harms the concurrency. Then we propose a new solution following this model. Our solution follows the workflow in this figure. We can see it is periodically distribute the tasks. In each round of the task distribution, we pull the seeds from all instances, partition them into unoverlapped, well, similar weight subset, and finally assign them back to each instance. We consider a fuzzing task to run one round of the mutation to a unique seed. We adopt a definition of seed uniqueness that balance between the effectiveness and the conservativeness. In our solution, to determine the uniqueness of a seed, we consider the edges that their hit count covered by the seed as a criteria. For example, showing in this figure, when seed 1 and seed 2 both exist at the same moment of the task distribution, we will consider seed 1 non-unique since seed 2 has all the edges of seed 1. Now let's talk about how to pick a unique seeds while running the task distribution. In each round of the task distribution, we pull all the seeds from each of the instances and rerun them with dynamic tracing. We gather the edges covered by each instance, we then compute the intersection among the edges from all the instance. We design a greedy algorithm to provide edge coverage-based task distribution. We aggregate the edges into a topo sorted CFG. We select the seed that cover the maximum number of the edges remaining on the CFG. If multiple seeds satisfy this condition, we will pick the youngest one. To better illustrate our distribution algorithm, we can see that from this figure. When we pick a seed for leaf nodes 4 to 8, we favor the seed 4 over seed 2. Because seed 4 is more recently generated, this prevents the peak of the seed 2 and avoid the overlap. This algorithm involves multiple heuristics, which strive for fewer overlaps and better efficiency. First, we prefer the seed that cover more non-distributed edges. This motivation is to quickly consume the distribution space. The second one is we favor the newer seeds. The seeds newly generated have a higher chance to cover new edges than the older ones. The third one is we favor the edges that have larger depths on the CFG. This is to reduce the search space when picking the seeds. Because as we observed, the deeper edges are typically reached by the fewer seeds. Our design needs to periodically rerun the task distribution. However, a low frequency of the redistribution may not timely avoid the accumulated overlaps, while a too high frequency can lead to a waste of the resource. In our design, we adjusted the scheduling of the task distribution based on the increase of the edge coverage. We start the first round of the distribution after the first hour, and we rerun it once the new edge coverage growth reaches 10%. We have implemented our solution called AFL Edge on top of AFL and LLVM. We created new tools to collect the edge coverage, a new scheduling system to distributing the fuzzing tasks. We also customize AFL to confine the fuzzing task on the instance. We prepare a group of 9 real-world benchmark programs. Details about the program are presented in this table. We run the vanilla AFL as the baseline of our evaluation. To compare the AFL Edge with the existing solutions, we also run PFAS and PAFL on top of AFL. The direct goal of AFL Edge is to reduce the overlap among instances. To measure this goal, we consider the number of the seeds that are disabled from each instance as a metric. As shown in this table, our solution can effectively reduce the potential overlaps in the parallel mode. We measure the number of the edges covered in the tests. In this table, we present the increase of the edges coverage brought by AFL Edge to AFL at the end of a 24 hours test. We can see AFL Edge can consistently improve the efficiency of the edge coverage of AFL, regardless of the benchmark and the number of the instance. We examine whether the AFL Edge and AFL are exploring the different edges. So technically, we measure how many of the edges covered by AFL are also covered by AFL Edge. We show the result in this table. We can see AFL Edge covers more than 95% of the edges that are covered by AFL. Considering the randomness, we believe such a result strongly support that AFL Edge largely preserves the behavior of the vanilla tools and does not significantly affect the fuzzing. To validate our hypothesis that the frequency of the distribution can be affected by the effectiveness of our solution and demonstrate our dynamic approach, we perform another experiment where we run 1 round of the distribution per 1 hour, per 2 hours, and per 4 hours. In this table, it shows that the frequency of the distribution truly makes a difference, and our dynamic adjustment indeed outperform the solution with a fixed frequency. We conducted another experiment to compare our algorithm with existing seed distillation algorithms. We run this algorithm on 1,000 random seeds from each of our benchmark program and conduct the number of the picked seeds. And count the number of the picked seeds. As shown in the table, our algorithm reduces more seeds than other existing algorithms in every benchmark program, demonstrating the better effectiveness. In the course of the evaluation, the fuzzing tools also trigger many crashes. As shown in this table, we can see the AFL edge triggered the 6,792 unique crashes, and the 14 previously unknown bugs, outperforming both PFuzz and PAFL. Moreover, all the bugs detected by PAFL and PFuzz are also detected by our solution. So, in conclusion, this paper focuses on the problem of parallel fuzzing. It presents a study to understand the limitation of the parallel mode in existing gray voxel fuzzing tools, and propose a general model to describe the parallel fuzzing. This model distributes the mutually exclusive but similar weighted task to different instances, facilitating the concurrency and also fairness across the instance. Guided by this model, we present a novel solution to improve the parallel mode in AFL. We have implemented our solution on top of AFL, and we have evaluated our evaluation on 9 widely used benchmarks. Our evaluation shows that our solution can significantly reduce the overlap and hence accelerate the code coverage. Thank you so much.